Okay, so just a reminder, this is a continuation of 5.4.2 quiz review. This is part 2 of 2. Okay, so let's start this one over. Your spacecraft lands, okay, you drop a 1.3 kilogram wrench from 5 meters above. This is the circumference. This is the time. Okay, and so what we had done on the last part was we made circumference is equal to 2 pi r. So I have 62,400 times 2 times 3.14 times r, and I'm solving for r. We're going to need it at some point. So I get 9936.3, and this is in kilometers. So I have to change this into meters, and then I put it in scientific notation. Okay, let me change colors. Okay. Then the next thing I did, this is the first thing I did. The next thing I did was I used one of our kinematic equations to find the acceleration of gravity, and I used this one. Should look a little bit familiar. VO is 0, so 5 is going to be x. I have 1/2. I'm solving for a, and t is that. So a is 15.20 meters per second squared. Okay. Why did I need that? Good questions. All of them good questions. So then what I did, let me change colors again, was I said, okay, I'm going to set Fg equal to the force of weight, which means I have G, M1, M2 is equal to mg over r squared. My m's, one of them is going to cancel out, so I end up with, oh, I know why, because I need this, that's gravity. Gm over r squared. And then I solve for m, which is the planet's mass. So solve for m, and I get m is equal to gravity r squared over big G. So this is where I'm going to put my 15.20 times my 9.9 times 10 to the 6th squared over 6.674 times 10 to the negative 11. And I get for a mass 2.23 times 10 to the 25th, which is A. Where's my cursor? I can't see it. Where am I? There I am. Okay, sorry. A. All right, next problem. Okay, January 2005, the Huygens probe landed on Saturn's moon Titan, the only satellite in our solar system with dense atmosphere. Titan's diameter was this. Okay, so one of the first things I did so that I don't use that number is I know that radius is equal to diameter divided by 2. So I got this, and then I know this has to be converted into meters if I'm going to use it in any of my current formulas, so that's meters. Okay. Its mass is this. The probe weighed this on Earth, which means it weighed, if I did this, the gravity would be 9.8. Aha. Right, so to find my mass of the probe, I went ahead and plugged in and that's what I got for the mass of the probe. Let me change colors. So I went ahead and used this over r squared. And I have the mass of the planet, which is 1.35 times 10 to the 23rd. I have the mass of the probe, which is 318.36, all over the radius, 2.575 times 10 to the 6th squared, and I get 432.597 newtons, which is going to end up being B. Okay, this one was a little weird, but I finally figured it out. So there's a lot of derivation stuff, so I'll show you how it goes. The mass of the moon is 1/8 the mass of Earth, and its radius is 1/4 that of Earth. The acceleration due to gravity on Earth's surface is a number we've been using the entire semester. What is the acceleration due to gravity on the moon's surface? So what I did was I said, okay, I set mg equal to gm1 m2 over r squared, and which cancels out one of my m's, so I have g is equal to gm over r squared. So on Earth, this is GE is equal to RE. And then on the moon, I have GM is equal to GM of the moon over RM squared. That one's squared too. And then I have G of the moon is equal to G 1/81st mass of Earth over 1/4 RE squared. Okay, so then what do? I divide GM and GE. Okay, so this goes up like this. I have GM over GE is equal to G 1/81st ME over 1/4 RE squared over, so that's the moon, and then this is Earth. Okay, and then we're going to cancel some stuff. So this is going to go, this is going to go, this is going to go. So I end up with 181 over 1/4 squared, which is equal to 181 times 4/1 squared. Escape. And if I'm going to solve for the gravity of the moon, I'm going to have to get gravity of Earth over there. So I have, this is squared. So I have 16/81 times the gravity of Earth, which is 16/81 times 9.8, which is 1.936 meters per second squared. And that is C. Okay, next one. Asteroid 234 Ida has a mass of this, an average radius of this, okay, which we're going to have to convert to meters. What is the acceleration due to gravity? And then this is our constant. So the example I'm using in the lesson is gravity on Mars, and that's on page 36 of 49. And they have this great formula, which is that gravity is equal to gm over r squared. And it's derived from the original F is equal to gm 1m2 over r squared. And if you want to see the derivation from here to here, you can look here. But this is one of the formulas I would put on a note card or something to that effect. Times mass, which is 4 times 10 to the 16th kilograms, over 16,000 squared, which gives me 0.0104 meters per second squared. Now here's the deal. All of my answers are in centimeters per second squared. So I have to convert. So I have 0.0104 meters per second squared. I know that 1 meter is equal to 100 centimeters. So my meters are going to cancel, and I end up with 1.04 centimeters per second squared, which is going to be A, if I can find it. Where is my... There we go. All right, next one. Okay. This one we're going to use that same gravity formula that I had on the last one. So it's asking for acceleration due to gravity, and that formula is this. So my constant, my mass, is given in the problem. And I have to convert this to meters. So I have this squared, and I end up with this, which is B. Okay. Earth has a radius of this. What is the mass? So first thing I need to make this, convert this to meters. Okay, and then I'm going to use the gravity formula we used on the last two problems, because I know gravity on Earth, so I can plug that in. I can plug in my constant, -11. I'm looking for the mass of Earth, and I have the radius. So when I solve for the mass of Earth, I get that, which is C, closest to C. Do I have one more? I do not. That is it. Let me know if you have any questions.